Hi, everybody. This is Professor Monty, and today we're jumping into Chapter 4, which is probability. 4.1, we start with probability basics, so let's just define probability. Probability is the likelihood something will happen. And let's start off showing kind of a major thing that we're going to start with here. So if events are equally likely, so each of however many events that we have possible, any outcomes we have possible, if those outcomes are equally likely, what is the probability that one of them would happen? Well, see what it says here is the probability is what we call the F over N rule. F, the numerator, is the number of ways an event can occur, where N is the total number of possible outcomes. So for example, suppose you're at a party with one of your friends, and there's 10 people there, and one of you 10 people is going to be randomly selected. So there's 10 people at the party. And we're going to choose one of those people. Find probability, it's you. Since you're one of those 10 people, find probability you are chosen. Well, so we'll go right to that F over N rule. Well, there's 10 total people to choose from. And if everybody's equally likely, you're one of those 10 people. And so that's the probability you're going to be chosen. 1 out of 10. Sometimes I'll write it as a decimal, 0.1 or 0.1, however you'd rather write that. But if we write it as a fraction, we're always going to write it fully reduced. Okay, so let's take that one step further. Now suppose, same party, same 10 people, but you're there with your friend. What's the probability one of the two of you are selected? So find probability you or your friend are selected. Again, we just go to the F over N rule. There's still 10 people at the party. Everybody's equally likely to be selected, and there's 2 of you. So now it's 2 out of 10. So we could reduce that to 1 out of 5, or we could call that 0.2 or 0.2. And so it's just the same formula. So it's real basic, quick formula, and we're going to use this formula a lot. So let's talk about some of the properties of probability. So properties of probability, we'll just list them as properties. There's 3 main ones they give us. All probabilities must be between 0 and 1. That's one of the probabilities, and we saw the 2 we saw. We had 0.1 and 0.2. Clearly, each of those were between 0 and 1. If probability equals 0, that is an impossible event. Or an impossible outcome, if we want to say it that way. But 0 means there is 0 chance that's going to happen. And then 3, what does it mean if the probability is 1? So if probability equals 1, they have a term for that also. That is a certain event. It means it has to happen. And think about it, we can change these to percentages if we want to. So a probability of 0 would be 0% chance that it's going to happen. Okay, it can't happen. That's impossible. If the probability is 1, that becomes a 100% chance that it's going to happen. Well, we're certain that it has to happen. So those are the basic properties. Obviously, the closer the probability is to 0, the less likely it's going to happen. The closer to 1, the more likely it's going to happen. Okay, So those are the big ones. Let's look at some problems out of this section to kind of see what's going on. So let me go grab a problem. Let's see. We'll grab this one. Let's grab 415. Let's try to just copy and paste it in. Okay, so 415 says poker chips. A bowl contains 12 poker chips, 3 red, 4 white, 5 blue. If one of these poker chips is selected at random from the bowl, what is the probability the color is red? I'm going to do a little sneak preview, and we're going to do a P of red. That's going to stand for probability it's red. They actually don't define P of something until a later section, but I think that's clear enough. Well, guess what formula we're going to use? Since we only have one formula, you're right, it's F over N. So let's see. Remember, N, and notice that's capital N, is population size. So N is the number of poker chips that are in there, in this case 12. And F are the numbers that would satisfy the fact that it's red. Well, that has to be the red poker chips. There's 3 of those. And so all we do is reduce that fraction. We get 1/4 or 0.25. Either way is fine. Again, they will reduce it. If you put 3 12s in the program, it's probably going to mark it wrong. Okay, so just be careful of that. And you may want to practice some of these to see what the program will accept. All right, so part B, what's the probability it's red or white? Well, in that case, we just add up, again, it's F over N, of course, 12 possible, and we just add up, well, how many are either red or white? Well, there's 3 red and there's 4 white. So there's a 7 out of 12 chance that the poker chip will be red or white. Again, we can get a decimal if we want to. That's not going to be as nice a decimal, and I can't do it in my head, so I'll just leave it there. And then lastly, what's the probability that it's not white? Well, if it's not white, that's the same as saying what's the probability that it's red or blue? F over N. Let's see, how many red ones do we have? 3 red, 5 blue. So 3 plus 5. Again, the denominator is 12. So we get 8 out of 12, or 2/3. 0.67 if we round that to 2 decimal places. And so it's pretty easy. It's very straightforward. But let's do a couple more examples to make sure that this is really sinking in. We've got a good idea of what's going on. So let's jump in. We're going to pull out 426 as our next problem. There it is. All right, we'll paste that in here. Coin tossing. A balanced dime is tossed 3 times. The possible outcomes can be represented as follows. Here, for example, HHT means the first 2 tosses came up heads and the third tails. Find the probability that, and then they ask us a few questions. Let me talk about how they built those options in there. So let's think about what could happen. We've got 3 tosses. Well, it's possible that they're all heads. Or maybe just 2 of them are heads. Well, if 2 of them are heads, it might be the first 2. So we have to think, well, where could the tail be? The tail could be at the end, the tail could be in the middle, or the tail could be first. And so we see from that there's 3 different ways that we can get 2 heads and 1 tails. And then we just keep going. Now, that was 0 tails was the first one. 1 tails were the next 3. Let's do 2 tails. So where's the head? Well, head might be first and then 2 tails. Or it might go tails, heads, tails. Or it might go tails, tails, heads. 3 ways we can get 1 head and 2 tails. And then what about 0 heads? Well, that would mean they're all tails. Those are the 8 options they've listed. So even if they don't list them, we should be able to recreate that table. Okay, now let's go from there. A says exactly 2 of the 3 tosses come up heads. Well, let's mark that in blue. Exactly 2 of the 3. First of all, let's F over N, same formula. Now we'll go mark those in blue. let's see, exactly 2 of the 3 tosses are heads. Well, 2 heads, 2 heads, 2 heads, those are the ones that have exactly 2 of the 3 tosses are heads. So we just write that. There's 8 possible, we can count them, and 3 of those 8 have 2 heads in them. So that's our answer. For B, we go F over N again. Let me erase these blue dots. We'll do some new blue dots. The last 2 tosses come up heads. So if the last 2 tosses come up tails, it's not the first one, second one, third. Oh, this one, the last 2 tosses are tails, and this one. Those are only 2 that have the last 2 tosses tails. So this time, what is it? Well, it's 2 of the 8. Again, that's not reduced, so make sure you do reduce that. And again, you can say 0.25 if you want to. Any of these you can reduce to decimals. All right, let's see. C says all 3 tosses come up the same. Well, to erase those, how could they all come up the same? Either they're all heads or they're all tails. There's only 2 chances. So F over N, 2 over 8 again, just like the last problem. So 1/4. And then lastly, the second toss comes up heads. All right, let's see, let's erase those. The second toss heads. I'm going to actually circle these this time. The second toss comes up heads. Well, this one and this one, that one, that one. That's all. So as you expected, it's F over N. This time we get 4 out of the 8. That's a horrible 8. Let's erase that. It's 4 out of 8. That reduces to 1 out of 2. Hopefully that's not surprising to you, because this answer, this problem is just based on a single toss, just the second toss. Well, if you're tossing a coin, a fair coin that comes up equally likely heads and tails, what's the chance it's going to be heads? Well, it's 1 out of 2, which is what our answer reduced to. That's why it was 4 out of 8, because it's just based on that second toss, and so 1 out of 2. So pretty straightforward. I think that's pretty nice. We'll do one more problem in this section just to get another idea, and then we'll jump into the next section. Let's look at problem 431. There it is. All right, let's see. So we'll paste that one in there. 431, we'll paste it about here. It says the probability is 0.667 that the favorite in a horse race will finish in the money, meaning either the horse finishes first, second, or third place. In 500 horse races, roughly how many times will the favorite finish in the money? Well, this is going to be a common type of problem that they're going to ask you, and what you're going to do, it's going to be the probability times the number of chances, we'll say. And so in this case, we're going to say, oh, it's 0.667. And then the number of chances is 500. So I'm just going to multiply those together. And if essentially 2/3 of the time out of 500 races, it comes up. So 0.667, I'm just using my calculator, times 500. I get about, well, I get exactly 333.5. And oftentimes we'll round that to the nearest number. So we have to round up since we have that 0.5. So about 334 times in 500 races will the favorite finish in the money, first, second, or third place. And you would just do this according to what you have in the problem, what they ask you to round to. Okay. So that's the end of that section. Let's jump into the next section. We'll talk about events. All right. Now, events, we'll say an event is a collection of outcomes. And a single outcome could be considered an event. We could say the event that at the party of 10 people, you're chosen. But usually, oftentimes anyway, we'll talk about event as several different options. So we can list an event as, hey, what if the person gets picked is wearing black to the party, or they have a hat on, whatever it is, that might include several people and they all share some sort of characteristic. Okay, so that's the idea of an event. What I'm going to do is I'm going to show what's called Venn diagrams, capitalized because it's named after a person with the last name of Venn. And what these are pictures to represent events. So for instance, what they're going to do is they're going to draw a circle for each event. And this will just be the event E. And then they put it inside a box. So the box is, inside the box is everything that can possibly happen. And we're saying, well, within that box of everything that can happen, event E might happen. So this is just a picture of event E. And what I would typically do is I would shade this box in. The E doesn't show up as well. Here, let's get the black pen and overwrite it so it'll show up better. But that shaded area represents the fact that event E happened. Now, what if E doesn't happen? So we'll put an E here again, put the box around it. And oftentimes we'll call this not E. Well, what's that going to be? Not in the circle, it's everything else. So we would shade everything outside the circle. And that would represent the event that E did not happen. All right, so what if we have a couple of different events? So what I'm going to do is I'm going to do two circles. I actually wanted to do that in the black pen so it's consistent. So there's event A. Let's say there's an event B also. Now, if we're talking about that both A and B happen, what that's going to be, that's just this little overlap right here. That overlap would be A and B. So A and B means A happens and B also happens. So let's write this over here. So A and B, both A and B happen. Notice I can't shade this area right here. That would mean A happened, but B didn't happen. So we'll erase that. Okay, and then let's think about, we'll put events A and B up here again. There's a little bit bigger of a circle than I intended. Let's do another one. There we go. So there's A and B, just like last time. There's my box. Sometimes they call that the universe. Now, if I'm saying A or B, think of what happens. If A happens, everything in here gets shaded. If B happens, we also get everything in B. And so if we shade everything, that's A or B. So if we write that down, A or B, that means A happens or B happens. And notice I shaded the stuff in the middle, so I would say or both happen. Okay, so that's our idea there. Those are some Venn diagrams so that we can kind of understand what's going on. There's one more I want to show you since we have these up here. What if, and you may have asked this question before, how do we know those circles overlap? They may not overlap. If I've got something like that, there's no overlap. And in fact, if you're thinking about A and B, there is no A and B because they both can't happen at the same time. There's no overlap. What we say about this is A and B are mutually exclusive. And so here we'll kind of define that. Two events are mutually exclusive if they cannot happen at the same time. So for instance, getting a grade of an A and getting a grade of a B in the same class on the same test, those are mutually exclusive. You can't get an A and a B on the same test. You can either get one or the other. Okay, so those would be mutually exclusive. There's my definition of mutually exclusive. Okay, from there, I want to do a few problems here as well. So we'll kind of scoot that out of the way. Let me go grab a problem. We'll start off with 453. And we'll paste that one in. Let's see what this one's all about. All right, we're rolling some dice. Actually, we're only rolling one die, apparently. When one die is rolled, the following 6 outcomes are possible, 1 through 6. List the outcomes constituting A, the event comes up even. So if I'm doing A, we would write it something like this. If it's the die comes up even, that's either a 2, 4, or 6. So we usually put it in set notation. These are the possible outcomes to say that A comes up even. So for B, it says the event comes up 4 or more. So it comes up as a 4 or a 5 or a 6. C would say the event, the die comes up at most 2. That means it's 2 or less. So it can come up as a 1 or a 2. And then D would say the event comes up 3. Well, obviously the only thing in the set bracket is 3. Those are usually called braces, by the way, not a bracket. Okay, so that was pretty quick. Let's look at 457. All right, so we'll paste this one in here. And watch this. This is why that problem is so quick. 457 says, hey, look back to 453, which we just did. For each of the following events, list the outcomes that constitute the event and describe the event in words. Well, so not A. Well, notice A, just looking right above it, was 2, 4, or 6. If it's not A, that means it has to be anything that's not 2, 4, or 6. So that means it has to be 1, 3, or 5. And to write that in words, we could say event die is not even. And of course, if you wanted to, you could say the event the die is not, or the event the die is odd. But I wanted to go with their wording of the not. Part B says, well, what about A and B? Okay, remember that and says it has to be in event A and it also has to be in event B. So we look at A and B for what they have in common. They don't have a 2 in common. They do have the 4, they do have the 6. Notice I don't have to go down to the B to see if there's anything else in B that's not in A, because if it wasn't in A, it's not going to be in both. So once I look at everything in A and see which ones are in B, I've got all my answers. So A and B is going to be 4 and 6. And if we wanted to say that in words, we could just say event die is, well, A and B, even and 4 or more. Die is even and 4 or more. And clearly, both 4 and 6 satisfy both of those conditions. All right, let's go to C, which is our last one here, obviously, B or C. And remember with or, it has to be either in B or in C or in both. So what I get to do here is I get to choose everything that's in B. So if it's in B, it's either 4, 5, or 6. But I also get to take it if it's in C. So I get to take 1 and 2. Now these didn't have any overlap, right? There's nothing common in both B and C, which means they're mutually exclusive. But if we had, say, 4 was part of event C, we'd still keep it because being in both is okay. So anyway, we're going to list this, and I'll go in numeric order, 1, 2, 4, 5, 6. And then in words, we would just say something such as the event, and then we just look at the words. It's 4 or more, or it's at most 2. Event die is 4 or more, or at most 2. And so that would be the wording. Okay, so that's all the die problems we're going to do in this section, but we do have one more problem in this section that I would like to do. So humor me, we're going to go to problem 464. Obviously, we're just going in order of these. And as you can probably see, we've only got one more problem in this section or in this lecture that we're going to do today. So we'll only come back to this one more time because we've already copied everything else. So we'll paste that one in. Ooh, NBA Finals. The NBA Finals of basketball is played in a best-of-7 series. The number of games necessary to decide a winner can range from 4 to 7 games. So it's best of 7. So if you win 4 games, there's only 3 other games left. The other team can't win the series. You win the series. So you may win it in 4 games, 5, 6, or 7. Okay, so we look at the table. It says for one of these series selected at random. So we're randomly picking one of these series, and we want to know how many games were required to win the series. Event A is the event that the NBA Finals was decided in 5 games. Now, what we're trying to do is we're trying to find these probabilities. So for this problem, let's say probability of A. Well, the probability of A is the probability that the NBA Finals was decided in 5 games. Again, F over N rule. Well, we have to figure out how many games there are. I'm just going to add these up on my calculator. So we've got 8 plus 15 plus 24 plus 16. And I've got 63 games. That was the sum of X. Okay, so that's my total frequency. And so I've got 63 series. Well, out of those 63s, the one that were decided in 5 games were 15 of them. And I do know 3 goes into both of those. Rather than reducing this, I'm just going to plug it in my calculator. So 15 divided by 63, and it's about 0.238. I like 3 decimals. When I round off any of these, I need to round off because if I change that to a percentage, 23.8%. So personal preference, oftentimes the authors will do the same thing. All right, let's look at the probability of B. The event the NBA Finals was decided in at most 5 games. So what they're saying here, that's the probability that the frequency, not the frequency, we will just say the probability of the series, we'll just call that X, was at most 5 games. At most 5 games means less than or equal to 5. Well, if we look at what that means it's the probability that X equals 4 or X equals 5. And oftentimes we'll just write that as the probability of 4, 5. That's fine notation. Well, F over N, our good friend. So the probability it's 4 or 5, we're just going to add those up. 8 plus 15 divided by that same 63. So 23 divided by 63. Let's see what that is. 365, 0.365. Sometimes they want the exact percentage, so you'd leave it as reduced fraction, but oftentimes they'll just have you round it off. Again, I like the decimal in these because the 36.5% makes more sense to me than, 23 out of 63. I don't really have a good feel for that unless I do the math. And then we'll finish off with probability of C. The event the NBA Finals was decided in at least 5 games. Well, that means the probability at least 5 games is 5 or more, which is the probability that it's 5 or 6 or 7. We'll use the or in there instead of the comma so we don't have any confusion like we did before. And I may want to say up here so that there's no confusion. That's a 4.5. What's going on there? So we may say 4 or 5. Notice these are just mutually exclusive. So the series ends in 4 games or 5 games or 6 games or 7. It can't end in 2 of those at the same time. We can't say, oh, this year it ended in 4 games and in 6 games. That makes no sense. So we're just going to add those up. We're actually going to see this as a formula very shortly. But again, F over N. So I'm going to say, oh, 5 or 6 or 7. Well, there was 15 that were 5 games, 24 that were 6 games, and 16 that ended in 7 games. And again, it's over 63. We can add those up. 15 plus 24 plus 16. I get 55 out of 63. Which, if I do that division, it's about 87.3%, 0.873. Notice all these decimal numbers that we got were between 0 and 1, just like the property told us in the last section. Okay, done with that section. Let's go in and we'll jump into this last section for the day. I don't need that at all. So we'll go back here. We'll go into 4.3, some rules of probability. So let's look here. So this is where they introduce that P notation, and they say, hey, if I write P of E, that means probability event E occurs. Probability event E occurs. And we used it in the last section, so that doesn't shock us, I hope. Okay. So that's what they start. They give us a rule. It's called the general addition rule, and we actually used this in the last section. Remember when we had more than one event that might happen, and so we just added the events up? Well, that's the general addition rule, and it says this. Now, here's the general rule. We have to be careful. I'm going to draw you a Venn diagram again. This is the probability of A or B. Now, here's the problem. We just added them up, and we're going to see something about that. But look at this picture. If that's event A and that's event B, and I talk about, well, what constitutes event A? Well, it's all of this. What constitutes event B? Oh, it's all of this. And I have a problem there. My problem is that part in the middle, which we call A and B. We counted that twice. I counted it in A, but I counted it again in B. And so what we need to do is we need to take one of those out of there. So the general addition rule says it's the probability of A, that gives us all of that circle, plus the probability of B, that gives us all the second circle. But then again, I've counted the stuff in the middle twice. So what I have to do is I have to subtract one of those away. So it's minus the probability of A and B. I still have one of them. So for instance, if I counted the blue lines, I took out the green lines just in that overlap. And then I've still counted everything once. So essentially what I've ended up with is, let's look at it this way. Say I counted A here, and then when I counted B, I only counted this much, essentially is what I did. So there's A and B. That gives us the total. So that's my general addition rule. Sometimes, though, they don't overlap. We already looked at that. So what happens if they don't overlap? We have another rule. It's called the special addition rule. And this is the one we were using in the last section, actually. The special addition rule says, if A and B are, if they don't overlap, mutually exclusive. Then probability of A or B. Notice it's called the addition rule because if we have an or, we change it to a plus. That's just the probability of A plus the probability of B. We don't have to take out the probability of A and B because if they're mutually exclusive, they don't overlap. And the probability of A and B would be 0. So that makes it easier. That's the special rule. Why is it special? Because it only works if the events are mutually exclusive. All right, so let me show you an example of one where they're not mutually exclusive. So say, example, ask 20 coffee drinkers. Do you put cream in your coffee? Do you put sugar in your coffee? Or do you put both in your coffee? Do you add cream? We'll call that C. Sugar, S, or both? B. Now, realize if you add both to your coffee, then when they say, hey, do you add cream? You have to say yes, because you do add cream. When they say, do you add sugar? You're going to say yes, because you add sugar. Do you add both? You're going to say yes. So if you add both, you say yes all 3 times. Okay, if you just add cream, obviously you just say yes to the cream. Okay, so let's draw a Venn diagram. Are these going to intersect? Yes, we know they intersect because some people add both. So this will be our coffee drinkers. This is they add cream. This will be they add sugar. So this is cream, this is sugar. Now, I'm not going to do a different circle for both because remember the people that add cream and they also add sugar are in there. Where are they? They're actually right here. Those are the people that add both. What are these people out here? Those are any coffee drinkers that don't add cream and they don't add sugar. They just drink it straight. This is the way you gave it to me. Okay, so let's get rid of that, but that's what this is. So what we're going to do is we're going to fill in this Venn diagram. How do we do it? Well, the easiest way to do it is we've got our cream and our sugar. We'll put that up there. I'm going to start with how many add both. So let's say we did this. So the number, and let's say the number that added cream out of these 20, let's say 8 people said they added cream. We'll say the number that added sugar, looks like a 5, were 10 people said they added sugar. And 6 people said they added both. Now notice we can't add just all those up because we're going to get 24 coffee drinkers. We only asked 20 coffee drinkers. So how do we start? We start with that both. That both we know is right in the middle. So we know that has to be 6 people added both cream and sugar. So now can I put the 8 right here? No, I cannot. We know 8 people put cream in their sugar, but I've got an 8 in there and a 6 in the same circle. Well, that would mean 14 people put cream in their sugar, and we did not have 14 people put cream in their sugar, cream in their sugar, cream in their coffee. So what I have to do, this number right here, I was still on the eraser, unfortunately. This number right here is going to be all the people that put cream in their coffee. So it's the number put cream minus the number that put in both. So I'm going to say, well, 8 people put in cream, but 6 of those also put in sugar. They were counted twice. So there's only 2 people that put in cream and not sugar. Notice now if I add the 2 and the 6, I get 8 in the cream circle, and that's what we said there was. Now, similarly, what's going to go in that part of the sugar circle that's not the 6? Well, they have to add up to 10. So you may just say in your head, oh, that has to be 4, which is exactly right. So if I add those up, I'm going to say, okay, what goes in there? Well, it's all the sugar drinkers, all the people that add sugar to their coffee, minus the ones that add both. And so in this case, it's going to be 10 minus 6, which was that 4 we talked about. So I put a 4 in there, and to double check, let's add up in the sugar circle. 6 plus 4 is 10. Okay, I know that we do have 10 in the sugar circle. We have 8 in the cream circle, and both we have 6. So then I could use that to answer any questions. And oftentimes, they just want you to go that far. Now, there is one more question to that. How many didn't put in anything in their coffee? Well, that's going to go out here. Because notice, if we add those up, we get 12 people. We talk to 20. So what we do is we start with the 20. We subtract out the 2. We subtract out the 6. And we subtract out the 4. And we end up with 8 people here that just drink their coffee without cream or sugar. And notice we add up the 8 and the 2 and the 6 and the 4, that gives us 20. So that did account for all the people. Another way to write this, we could say it's 20 minus 2 plus 6 plus 4. Because now it's 20 minus 12, which is an easy way to get to 8 in your head. But now that's a completed Venn diagram. We've accounted for all the people, and we've accounted for all the different possibilities. Okay, so let's take a problem out of the book. Notice what we used here. If I do this before we take that problem out of the book, if I say, let's do one more. What's the probability they add? What's the probability, not A, what's the probability that they add cream or sugar? Well, what do we have to do? We have to say, well, these are not mutually exclusive. So what I need to do is I need to use the general addition rule. I'm going to write this down here so I can write it as one big long string. So the probability they drink cream or sugar, well, it's probability of cream plus probability of sugar minus probability of both cream and sugar. Notice that's the same as saying probability of both. Well, what's the probability of cream? Well, the probability of cream, what did we say added cream? 8 people. So that's going to be its probability, F over N again, right? It's 8 out of 20 people added cream. How many people added sugar? Well, we can look at, 10 people. Plus 10 out of 20. And then what's the problem? The cream and sugar we counted twice. So we have to subtract that away. That's the 6 out of 20. And now we get 8 plus 10 is 18, minus 6 is 12 out of 20. And then we can reduce that however we want to do that. Let's see, it's 6 out of 10. I guess we can reduce that also. It's 0.6. I'll just leave it as 0.6. Instead of a reduced fraction, we could reduce it to 3/5 if you'd like to, but it's 0.6. And what was it? It was 12 people drank cream or sugar. So notice this 12 here is the 2 plus 6 plus 10. The 6 and the 2 plus 6 plus 4. The 6 and the 4 is 10, and the other 2 gives us 12, same 12. So we could have actually just looked up in the picture now that we have it and just added the 2 plus 6 plus 4. But I wanted to show you here the general addition rule. Okay, let's go into the next one. It's an example you may have guessed of the special addition rule. So we'll go in, we have one more problem in here to take out. Let's grab this one. We'll paste that in. We'll be looking good. All right, let's put that right there. Religion in America. According to the Religious Landscape Survey sponsored by the Pew Forum on Religion and Public Life, a distribution of religious affiliation among U.S. adults is shown in the following table. And so they give the affiliation, Protestant, Catholic, Jewish, Mormon, or other, and the relative frequency. So that's already the probability. Notice we haven't even talked about that, but probability is another word for relative frequency that we've seen before, chapter 1. All right, so find the probability that the religious affiliation of a randomly selected U.S. adult is Catholic or Protestant. Well, for A, we're going to say, what's the probability? And they're all different letters, so let's just go C or P. Now, notice they list Catholics and Protestants separately because what they're saying is these are mutually exclusive. So in this case, I can use the special addition rule. Special addition rule, since mutually exclusive. And so the special addition rule just says essentially probability of A or B is the probability of A plus probability of B. There is no minus probability of A and B because those would all be zeros. So the probability of C or P, it's literally probability of C plus probability of P, but we did this in the last section where we just added them up. So it should make sense because that's all we did in the last section. So this rule, when we say or, it's like, oh, well, that makes sense. That's what we're doing in the last section. So probability of C, that's 0.239, plus probability of P, 0.513. I'm just pulling those straight out of the chart that they gave us. And then 0.239 plus 0.513, we get 0.752. That's the probability that they were one or the other of those two. And then it says probability not Jewish. So probability not Jewish means probability of any of the other ones. So let me show you two ways to do this. That could be the probability, if we go in order, that they're Protestant, or the probability that they're Catholic. I'm just going to change right to the rule, or they're Mormon, or they're another religion, probability of other. And then I can just add all those up. So probability Protestant, 0.513, plus Catholic, probability 0.239, plus Mormon, probability 0.017, plus other 0.214, and then I can just add those up. That's why we have calculators. 0.513 plus 0.239 plus 0.017 plus 0.214, and I get 0.983. And let me show you a little trick. There's a formula for when we're finding not something, and it's called the complement rule. And it would say this: probability of not A is going to be 1 minus the probability of A. What in the world does that mean? Well, let's think about it. A either happens or it doesn't. So if I look at the probability of A or not A, that's a certain event. It either happens or it doesn't. There's a 100% chance that it's either going to be A or it's not. So those have to add up to 1. So if I do probability of A plus probability of not A, those are clearly mutually exclusive. They can't both happen at the same time. I get a 1. Well, algebraically, if I just subtract P of A from both sides, what am I going to get? I'm going to get the probability that it's not A is 1 minus probability that it is A. And you could subtract the other way, so that's the formula. Or if I subtracted probability of not A, I could say, oh, the probability that it's A is 1 minus the probability that it's not A. So I can use that either way. We'll just kind of box that as well. And so for this problem about Jewish, what's the probability they're not Jewish? Well, we could have said probability not Jewish is 1 minus the probability that they are Jewish, which is 1 minus, well, the probability they are Jewish was 0.017. And if I subtract that, I get 0.983. And lo and behold, it's exactly what I got when I added those up. So a lot of times when there's only one that you're excluding, you can just do 1 minus the probability that that one happens, and that'll give you the probability that it doesn't happen. So anyway, that's the end of the lecture for today. Practice these, and then next time we'll just see some more probability things before we finish this chapter. All right, so best of luck to you. We will talk more later.